All right, we continue chapter 2, section 2, looking at 2.3 to 2.5 by examining some organic acids and bases. Okay, so the first and most common acid that we see, it's right there in the name, right? Carboxylic acid. And you are going to need to learn how to quickly identify these things based on their structure, which we talked about at the end of General Chemistry 2 last semester, right? If you're using a condensed formula, you can look out for COOH, C-O-O-H, right? That's a quick indication of a carboxylic acid, but this is what the structure looks like. Carbon double bonded to one oxygen, as we see here, single bond to an OH, right? And then another alkyl group over here, just a general, we'll call it an R group, you'll see in a few chapters, right? That could be anything else over there. Okay? And this is the acidic hydrogen. When it acts as an acid, this is the hydrogen that is lost in carboxylic acids. And these guys have a pKa in the range of about 3 to 5. You see the exact pKa's here. You do not have to worry about memorizing those. Rather, just know the range for carboxylic acids, 3 to 5. We also have alcohols, which are ever so slightly acidic in water. Okay? They are much weaker acids than carboxylic acids. Notice the difference in pKa, right? Factor of 10. And that's a logarithmic scale. So that's 1 with 10 zeros after it. Less acidic than carboxylic acids are. Okay. We identify alcohols by the OH, right? Methanol, ethanol over here, right? The OH. And again, that H is the acidic hydrogen. We also have amines in organic chemistry. We deal with these all the time, right? Ammonia is the most basic amine, NH3. Replace one of those H's with an alkyl group. Then you get other types of amines. Okay. Here we have methylamine, you can have ethylamine, etc. And notice that jump in pKa. Now we're in the 35 to 40 range. Okay, so amines on their own are not acidic. In fact, amines are basic with that high of a pKa. But if we protonate them, right, we move from something that's a common organic base. You'll see amines being used all the time as bases. But if we give them an extra proton, protonate them, we get a protonated amine, and these things are again acidic. Notice the pKa range here, right? 10 to 11. So if we have that, these protonated amines are now more acidic than alcohols are, because remember, the lower the pKa, the more acidic something is. Right? And that should make sense, because remember what we learned about conjugate acids and bases, right? A stronger acid means a weaker conjugate base, which would be a key idea here. And let's look at the ideas here, right? pKa of 10.7, right? This is more acidic than here, pKa of 11. So this tells me that protonated methylamine here is a stronger acid than what we have over here, right? And if it's a stronger acid, that means that this would be the weaker, sorry, I had my cursor in the wrong place, move it over. If this is the stronger acid, that also means that methylamine is a weaker conjugate base. So keep those ideas together. Stronger acid, weaker conjugate base. Stronger base, weaker conjugate acid. Okay. We also have protonated alcohols and protonated carboxylic acids. These are not as common as protonated amines, but if you encounter them, they are exceptionally strong acids. Notice now the pKa's are negative, which is fine. We'll see that all the time. Don't freak out if you see a negative pKa. Okay, protonated alcohols, protonated carboxylic acid is just an extra hydrogen. Here we have 2 protonated alcohols. Here are protonated carboxylic acid. Note where the proton goes. It doesn't go to OH2 over here. And negative pKa's, super strong acids. Okay. Which is interesting because we saw that an alcohol can act as an acid on its own, a normal alcohol, or it can pick up an extra proton to become a protonated alcohol. So that means that an alcohol can behave as both an acid and a base, which is similar to water. When we first introduced acids and bases, we said that water can act as an acid or a base. Alcohols can do the same thing. And this is a huge slide, not only for the understanding of acids and bases and what goes on in chapter 2, but because this is the first time that we see curved arrows. this semester. And those curved arrows are going to stick with you for the next 2 semesters of organic chemistry. A hugely important slide here. What these curved arrows indicate are bonds that are broken and then bonds that are later reformed as we go from reactants into products. And the reason they're curved like that and even a different color on this slide is to differentiate them from reaction arrows, which are these in the middle that separate reactants and products. Notice the 2 barbed arrow on the arrowhead here means we're moving 2 electrons, right? A pair of electrons here, a pair of electrons there. When we get to chapter 12, we'll actually see these arrows with just 1 hook on the side, 1 barb. That means we're just moving 1 electron, but that means we're dealing with radical species. Okay. And these arrows always start at the electron donor and move to the electron acceptor. So here in this case, we're moving from a lone pair on the base to the proton on the acid, which is the general scheme that we have for all acid-base reaction. Curved arrow points from the electron donor to the electron acceptor. Important slide. Make sure you know what's going on here on slide 17. On the top, we have methanol acting as an acid with hydroxide. And here we have methanol acting as a base with hydronium. Okay. So notice what the arrows are showing, right? That lone pair of electrons picking up the proton to form new bonds. Okay. And this, if there's a bond that breaks, we need to show that as well. Okay. Great. And then we see the same thing with carboxylic acid. So spend some time here on slide 18 and make sure you understand how carboxylic acids can behave as acids and less commonly when they can behave as bases. And here you see the different size arrows, right? Here, carboxylic acid and hydroxide, the products are favored. Here, the carboxylic acid and hydronium, notice the arrow there, the reactants are favored. We see it with amines as well. They are more commonly bases, but under harsh circumstances, they can act as acids as well. So those curved arrows are really important to understand and be able to draw them. So know what they're dealing with, okay? If we have an acid-base reaction, arrow is drawn from the lone pair on the base to the proton of the acid. Make sure it's curved. Emphasize the curve if you have to. Then we use a second arrow to show, right, with the electrons that are left behind in a bond that was previously going to that proton, where do they go? And they're typically just going back to the other atom that was sharing in that bond, but not always. And we have to use those to track the bonds that are formed and broken. This is the beginning of drawing mechanisms, which is a fundamental part of organic chemistry. Okay, so that's an important slide. Knowing how to draw those arrows is huge. Understanding this table as well, right? Remember I said earlier, you can know the approximate ranges for these guys. If it's protonated alcohol or carboxylic acid or water, negative pKa, incredibly acidic. Carboxylic acids, 3 to 5, protonated amines, 10 to 12, right? Alcohols and water, about 15. And then the only thing that's not on this slide, because they're not acids, they're bases, are amines, not protonated, just the standard amine, which hover about the 35 to 40 range. You have to know these pKa's to know quickly if things are acting as acids or bases, which is why we can quickly approximate them. You don't have to know the decimal point, right? As soon as you have that knowledge, you know how these things will react with one another in solution. Yep. And that comes down to predicting equilibrium as well. Does it lie to the left? Does it lie to the right? Okay. Because the stronger acid, the thing that has the lower pKa, is the thing that's going to act as the acid, right? That's going to control the reaction. So if I look at these pairs of reactants, right? HCl, pKa -7, that's acting as an acid. Over here, water, we don't typically think about as being as an acid, but with a pKa of 15.7 compared to the amine with pKa of 36, now water will act as an acid, right? We use that to predict the products of a reaction, keeping in mind that a reaction is in equilibrium. It can go either way, left or right, depending on the conditions, just like how water can act as an acid or a base, depending on the conditions. So that brings us to predicting the position of equilibrium, a fundamental idea from chapter 2. Okay. Equilibrium is going to favor the formation of the weaker acid. Okay, so the weaker acid is going to be formed because the stronger acid is acting as an acid. Okay. That gets us to a lower energy state. So what we do is we look at both sides, identify what is acting as an acid when they come together, right? And then we use that information to predict which way the equilibrium lies. The equilibrium is going to point toward whatever has the higher pKa because that is the weaker acid. We see it here, carboxylic acid around 5, protonated amine around 10, right? Equilibrium lies, points toward the right, the weaker acid. Over here, ethanol, pKa of about 15 to 17 versus a protonated amine around 10. Here we're pointing towards the higher pKa of the acid. Looking at just the acids, not the bases, right? Identify the acids, label the pKas. That's why you have to know this table back here, right? Know this table. And then the equilibrium arrow, it's not 50-50, it points toward whichever has the higher pKa and therefore is the weaker acid. Okay. We finish with this equation. We can calculate the equilibrium constant by actually using those pKas as well, right? We take the reactant acid minus the product acid, their pKa values, right? And that is equal to the pKeq. So then taking 10 to the negative both of those values can give you the KEQ. Not something you'll necessarily be tasked with doing, just an interesting way, right? We're using this information already to predict where the equilibrium lies, and that ties into the equilibrium concepts that we would have learned in chapter 12 in general chemistry. So that wraps up these ideas from this second video. We will continue to build on these in the next series as we discuss acids and bases further.